Regression calculations are often called least squares. So what's that? It's the smallest possible sum of squared mistakes. We don't like to call them mistakes, so we call them residuals. The residual is the difference between an observed y and the predicted y for an xy pair used in the regression. Before any regression, the best estimate we have of y for any value of x is the average y. That's a flat line through the average x and average y. For these points, the average x is 4 and the average y is 5. At x equals 2, the predicted y is again 5, the average y. The observed value of y is 3.5. The residual, observed y minus predicted y, is 3.5 minus 5, which is minus 1.5. At x equals 4, the predicted y is again 5, and the residual is plus 1.5. At x equals 6, the observed and predicted y are both 5. The residual is 0. The sum of the residuals is also 0, which means all our mistakes even out. We'll try a line that might fit through the points better. The line still has to go through the average x and average y, since that is always our best information. We'll set the intercept at x equals 0, y equals 3. The slope will be 0.5 for the line to go through the average x and average y. The predicted y at x equals 2 is now 4. The residual is 3.5 minus 4, which is equal to minus 0.5. The predicted y at x equals 3.5 is 4.75, and the residual is plus 1.75. The predicted y at x equals 6.5 is 6.25, and the residual is minus 1.25. Again, the sum of the residuals is 0. In both cases, the sum of the residuals is 0. In fact, the sum of residuals will be 0 for any line that goes through the average x and average y. That means the sum of residuals doesn't show that one line fits better than any other. Squaring the residuals makes all of them positive and different for each line. For the flat line, the sum of the residuals squared is 4.5. For the line with slope equals 0.5 and intercept 3, the sum of the squared residuals is 4.875. Therefore, the flat line fits better than the line with slope 0.5 and intercept 3. The sum of the squared residuals is smaller. But we can do better. In this graph, the intercept and slope can be changed to see how the value of the residual sum of squares changes. Somewhere around intercept equals 4 and slope equals 0.25 seems to have the smallest residual sum of squares, around 4.05. This is one way to understand simple linear regression. We know the line has to go through the average x and average y. In this example, x equals 4 and y equals 5. That becomes a pivot point for the regression. We can move one end of the line up and down, and we can move it up and down until we minimize the residual sum of squares. We don't have to hunt for the best slope and intercept by moving the intercept. The slope and intercept given by the regression equations are guaranteed to have the smallest residual sum of squares of any possible line. This is the least squares solution. The sum of squared residuals has a lot of names. All of them are the same thing. One thing to notice about squared residuals is that points with large residuals have a much greater effect on the position of the line than a point with a small residual. A residual value of 3 has 9 times the influence of a residual value of 1. Since the residual sum of squares is a minimum, the regression sum of squares is a maximum, and the R square is the maximum possible for the observed data.